They say the flap of a butterfly's wings in Brazil could one day set off a tornado in Texas. It sounds poetic, even absurd, but it's not just a metaphor. It's a clue to something much deeper about how reality behaves. Our world runs on two strange modes: order and chaos. Sometimes, events unfold with clean precision, every cause linked to its effect like gears in a clock. But other times, the smallest, most innocent actions ripple outward in unpredictable ways, rewriting outcomes across vast distances and time. Somewhere between those two worlds lies the secret pattern of existence, the hidden code that governs how everything connects. And at the heart of this mystery sits one of science's strangest revelations: chaos theory, the discovery that within disorder there is structure, and within randomness there is reason. At first glance, chaos looks like pure disorder, wild, unpredictable, meaningless. But what if every flicker of randomness actually hides a deeper rhythm? What if nature's chaos isn't random at all, but quietly following rules too subtle for us to see? For centuries, scientists believed the universe was mechanical, a perfect system of causes and effects. If we knew every position and motion of every atom, we could, in theory, predict the future with absolute certainty. But nature doesn't seem to follow our tidy expectations. The movement of clouds, the crash of waves, even the pattern of leaves on a tree, they defied predictability. Nothing stayed perfectly ordered. Yet, hidden in that disorder, something remarkable was waiting to be found. Imagine playing a game called the Chaos Game. All you need is a blank sheet of paper, something to write with, and a die. Here's how it works. Start by marking 3 dots on the paper, like the vertices of a triangle. Let's call them A, B, and C. Also, mark another point within the 3 marked dots as your starting point. Now roll the die. If you get a 1 or 2, mark a dot between the starting point and A. If it's a 3 or 4, mark a dot between the starting point and B. For a 5 or 6, mark a dot between the starting point and C. For example, if you roll a 2, mark a dot between the starting point and A. Roll the die again. Let's say you get a 2 again. Now mark a dot between the last point you marked and A. Repeat this process. Keep rolling the die and marking dots accordingly. For example, if you roll a 4, draw a dot between the last marked point and B, and continue this process. After doing this for a while, you'll end up with what seems like random dots on the paper, meaningless scattered points. But here's the strange part. What if these seemingly chaotic dots lead to something unexpected? To see some results, we can ask a computer to do this. And when I tried one of them, the result was very shocking, because out of that randomness emerged perfect order. The dots formed a stunning geometric shape, a Sierpinski triangle, a pattern of repeating triangles that continued infinitely, no matter how far you zoomed in. Each point followed nothing more than the simple rule of the dice, and yet together they created a masterpiece of precision and balance. This game revealed something profound. Complexity doesn't always need complexity to form. Even the simplest instructions, repeated again and again, can give rise to incredible structure. That's the foundation of chaos theory. It shows that nature's most unpredictable systems, weather, rivers, populations, even the human heartbeat, can be generated from rules so simple, yet so sensitive, that the smallest change in their starting point can rewrite everything that follows. Scientists began to see this everywhere, in the swirl of a hurricane, in the branching of trees, in the pulse of neurons, patterns repeating within patterns, fractals, self-similar shapes that echo infinity itself. And what's most haunting is that this isn't limited to nature. Even our lives, the choices we make, the timing of events, the coincidences that shape our paths, might be following their own hidden order. The discovery of chaos shattered the old idea that the universe was purely predictable. It showed that order and randomness weren't enemies at all. They were partners in creating everything around us. A single roll of the dice, a gust of wind, a heartbeat. Each event, no matter how small, ripples through a delicate web of connections, influencing things we can't see or measure. And as scientists stared into this world of fractals, feedback, and infinite recursion, one question began to haunt them. If even chaos follows laws, then maybe nothing in the universe is truly random. Because sometimes the deeper we look into disorder, the more order we find hiding underneath. But if that's true, if hidden order really governs the unpredictable, then what happens when one small change, just one, shifts everything we thought we knew? If hidden order truly governs the unpredictable, then it means something astonishing. Even the tiniest change, a single breath, a flicker, a heartbeat, could alter the course of everything that follows. That idea became more than philosophy in the early 1960s, when a quiet mathematician and meteorologist named Edward Lorenz made a discovery that would change how science understood reality itself. Lorenz was studying the weather, perhaps the most unpredictable system known to humanity. He wasn't searching for chaos. He was simply trying to make forecasts more accurate. Using one of the earliest computers at MIT, he built a set of equations designed to mimic the atmosphere. It was simple enough to run on the limited machines of his day. 3 mathematical formulas representing temperature, pressure, and wind. One afternoon, Lorenz decided to rerun a simulation to double-check his previous results. He entered the same data as before, or so he thought, but instead of inputting the full 6 decimal places, he rounded the numbers slightly. The difference was microscopic, less than 1,000th. In theory, that tiny rounding error should have changed nothing. But when the computer printed the results, Lorenz noticed something shocking. The weather patterns began the same way as before, but soon they diverged completely. What began as a harmless rounding difference grew larger and larger until the 2 simulations had nothing in common. That's when Lorenz realized something profound. The smallest variation in the starting point could create enormous differences later on. He called it sensitivity to initial conditions, though today we know it by another name, the butterfly effect. It's the idea that the flap of a butterfly's wings in one part of the world could, through a long chain of interactions, set off a storm on the other side of the planet. Not because the butterfly caused the storm, but because the atmosphere is so delicately balanced that even the smallest disturbance can tip it toward a completely new outcome. This wasn't randomness. The equations Lorenz used were completely deterministic. They followed strict rules, but the results were unpredictable. That's the paradox of chaos. Systems can be governed by order, yet still be impossible to predict. The deeper Lorenz looked, the more he realized that this wasn't just a quirk of weather. It was a universal principle. Every complex system, the climate, ecosystems, economies, even the human brain, could behave the same way. Tiny differences at the start could amplify through feedback loops, spiraling into vastly different futures. Think of it like this. Drop 2 grains of sand onto a sand pile. One lands harmlessly, the other triggers an avalanche. The difference between them might be smaller than a fraction of a millimeter, yet one reshapes the entire structure. This sensitivity isn't just found in the natural world, it echoes through our lives too. A delayed train that makes you take another route home, a random conversation that changes your career, a missed message that alters your future. Every decision, every chance encounter ripples outward into outcomes you'll never see. Lorenz's equations didn't just describe weather, they described existence. But the story doesn't end there. Out of the chaos of his weather model, Lorenz found something else, something unexpected. When he plotted the results of his equations in three-dimensional space, he discovered a strange looping shape that never repeated, yet never escaped its bounds. It looked like a butterfly, or perhaps two wings of infinity. This became known as a strange attractor, a mathematical structure that governs how chaotic systems behave over time. Even though the system's motion was unpredictable, it still followed invisible pathways, pulled toward this intricate shape. That's what makes chaos theory so haunting. Beneath the turbulence, there's still form. Within unpredictability, there's still order. Every chaotic system, from weather to the beating of your heart, moves within boundaries shaped by these attractors. They don't repeat, yet they don't wander endlessly either. They exist in a delicate dance between order and disorder, structure and freedom. In a way, the strange attractor is nature's signature, the whisper of stability hidden inside uncertainty. But Lorenz's discovery also carried a warning. It revealed a limit, not of technology, but of knowledge itself. No matter how powerful our computers become, no matter how much data we collect, if a system is sensitive to initial conditions, perfect prediction will always remain out of reach. Because we can never know everything about the starting state of the universe, there will always be uncertainty no matter how small. The weather, for example, may be governed by physics, but because we can't measure every molecule in the atmosphere, its long-term behavior will forever escape us. The same applies to global markets, ecosystems, even human societies. They are all deterministic, yet forever unknowable. This realization rewrote how science thought about cause and effect. For centuries, determinism promised certainty. If we knew enough, we could predict anything. Lorenz shattered that illusion. He showed that certainty and chaos can exist in the same system, and that the smallest shift can rewrite the script of reality. The butterfly effect became more than a scientific principle. It became a metaphor for life itself. It reminded us that small things matter, that the universe is sensitive in ways we can't comprehend, that everything, from the beat of a heart to the orbit of a planet, is connected through invisible threads of cause and effect. And perhaps most intriguingly, chaos doesn't destroy order, it creates it. When systems move through turbulence, they often reorganize themselves, finding balance in new, unexpected forms. The edge of chaos is where new patterns are born, where nature experiments, adapts, and evolves. So maybe the flap of a butterfly's wings doesn't just change the weather. Maybe it's the spark that gives birth to every new possibility in the universe. Because in the end, the smallest disturbances may be the very reason order exists at all. But if chaos gives rise to structure, then what deeper truth is hiding beneath the patterns we see? In the late 20th century, a mathematician named Benoit Mandelbrot began to see something extraordinary. While studying the irregular shapes of nature, mountains, rivers, and clouds, he noticed that no matter how closely he zoomed in, the roughness never disappeared. The same patterns repeated at smaller and smaller scales, endlessly. He called these shapes fractals. A fractal isn't like the perfect forms of traditional geometry. It's not a circle, square, or triangle. It's a pattern built from repetition, where the small parts resemble the whole. Zoom in on a fern leaf, and you'll see tiny versions of the same leaf. Look at a coastline from an airplane, then from the ground. The outline is different, but the pattern is the same. Fractals are the geometry of chaos. They reveal that even in disorder there's self-similarity, a hidden order woven into the fabric of nature itself. When Mandelbrot generated the Mandelbrot set, a now iconic image of swirling infinite patterns, it wasn't just beautiful, it was profound. This single mathematical formula produced a structure so complex that no two zoom levels are ever identical, yet every part echoes the whole. It was as if nature had a blueprint, not of perfection, but of infinite creativity. And once scientists began to look, they found fractals everywhere. The branching of trees, the flow of rivers, the veins in leaves, the structure of lungs, the rhythm of heartbeats, all share fractal behavior. Even galaxies cluster in fractal-like patterns across the universe. Fractals aren't static, they're alive. They grow through feedback, the process where an output loops back into the system as input, creating continuous transformation. Feedback is what drives weather patterns, ecosystems, economies, and even your brain. In nature, feedback can stabilize or destabilize. A thermostat is a simple example. When it gets too hot, it turns off the heat. When it cools, it turns back on. That's negative feedback, keeping balance. But in other systems, positive feedback amplifies change, like how melting ice reduces reflection, which causes more heat absorption, leading to faster melting. Feedback is the heartbeat of chaos. It's how small effects spiral into complexity. Your mind itself is built from feedback loops. Neurons fire, send signals, and receive responses from other neurons, constantly adapting. Consciousness, the awareness of awareness, may even emerge from feedback's infinite mirroring, where the brain observes itself observing. So perhaps chaos isn't the opposite of order, but the foundation of life, a constant dialogue between what was and what could be. This is where we arrive at one of the most haunting ideas in science, the edge of chaos. It's the thin boundary between total order and total randomness, the place where systems are neither frozen nor falling apart. Too much order and nothing changes, too much chaos and everything dissolves. But right at the edge, just between stability and instability, systems become the most creative, the most adaptable, and the most alive. It's here that life organizes itself. Biologists have found that organisms, ecosystems, even cellular networks naturally tune themselves to this edge. It's where evolution thrives. It's where intelligence emerges. It's where matter begins to think. At the edge of chaos, patterns appear spontaneously, like ripples forming from still water when touched by the slightest breeze. It's where the universe plays, forever balancing on the line between structure and collapse. Think about it. Our heartbeat isn't perfectly regular. It has fluctuations, a sign of health. Our thoughts aren't linear. They branch, connect, and loop. The most dynamic systems, the human brain, the climate, the internet, all live at the edge of chaos. And maybe the universe itself does too. Because when you step back far enough, everything begins to look like a fractal. Galaxies shaped like spirals within larger spirals, clusters forming webs that echo neuron networks inside the human mind. It's as though the cosmos is one vast feedback system, aware of itself through the patterns it creates. Mandelbrot once said, "Clouds are not spheres, mountains are not cones, coastlines are not circles, and bark is not smooth." He was reminding us that reality doesn't follow the simple shapes we imagine. It thrives in complexity. And within that complexity lies beauty, not despite the chaos, but because of it. When you look at lightning branching through the sky, or a river carving through rock, or neurons firing across your brain, you're witnessing the same principle repeated through scales. Patterns born from disorder, feeding back into themselves, creating structure again and again. It's not randomness, it's creativity. It's how the universe learns to build itself. Chaos isn't destruction, it's genesis. From the unpredictable dance of weather to the neural storms inside your skull, chaos breathes life into the static. It's the pulse that keeps everything moving forward, the reminder that perfection isn't the goal of creation, evolution is. And maybe that's the hidden truth. The universe isn't a machine running on fixed laws. It's a living fractal of feedback, an infinite experiment forever exploring its own possibilities. Every storm, every spiral, every thought, each one is a signature of that experiment continuing. And somewhere within it all is you. A pattern within patterns, a mind born from the chaos that shaped the stars. So, the next time you look at the randomness of life, the unexpected turns, the storms, the uncertainty, remember this: it's not disorder you're seeing, it's the universe learning to create. Because beneath every flicker of chaos lies the fingerprint of infinite order. Thank you for watching this journey through the chaos that shapes our reality. If you found wonder in this story, help us continue exploring the mysteries of existence. Subscribe and join us again on Uncharted Odyssey, where discovery never ends.